Alright, so today we're going to talk about systems of equations. We started this in class last Thursday, but I want to go over and review a few things from 11.1, a review of some things we did cover, and then go over some definitions that we did not cover, and then we'll get into 11.2 and 11.3 in the next few videos. So a system of equations, just to give you the review the definition, is a set of two or more equations solved together. An example of a system of equations might be something like y equals x plus 1 and y equals negative x plus 3. We looked at some systems of equations last week, and so this hopefully isn't new to you, but we did talk about the idea that you can graph these and find the solution. If I were to plot the graph just very quickly, and I won't take too much time to do this, but the first equation here has a y-intercept at 1 and a slope. This is 1x, so the slope is 1 over 1. So go up 1 over 1 and continue that pattern on. And we can go down 1, left 1, and continue that pattern on and get a pretty quick graph here. The second equation is negative x plus 3, so we go with a 3y intercept, and then we go down. So this is a negative 1 slope, so we're going to go down 1 over 1, down 1 right, down 1 right 1, down 1 right 1, and so on, and then up 1 left, and draw that line. And what you'll find is that every point on a line is a solution to that equation. Every point on this other line is a solution to this other equation. But the only point that is a solution to both is the point that is on both, and that is the intersection point. So this point right here is the intersection point, and it occurs at 1, 2. Okay, so the solution to a system of equations is the intersection point. In this case, it's the point 1, 2. Okay, so the solution is the intersection point. Now, we saw a bunch of examples of that on Thursday, but what we didn't see were some other situations where the graphs don't intersect in the same way. Most of what we will see are graphs that intersect at one point. But you can also have other scenarios like this one where you have two parallel lines. Okay, we know that parallel lines never intersect. Parallel lines never intersect. And so if they never intersect, a system with parallel lines would have no solution. Okay. Also, another weird scenario is where you may have two copies of the same line. Okay? And if you have two copies of the same line, then every point on the line is an intersection point. And so, because there are infinitely many intersections, or infinitely many points on the line, you would say there are infinitely many solutions. Okay. Now, because these are the only three scenarios you can have, you can't have two intersections because you'd have to have the graph curl back around to the other line, and then it's no longer a line. So because these are the only three situations you can have, we have names for them. And I'll give you a couple definitions here. First one is a consistent system. Consistent systems have solutions. A very basic definition, but that would include the one solution case and the infinite solution case. Okay. Alright, so consistent systems have solutions. The inconsistent systems have no solutions. Okay. Inconsistent systems have no solutions. That would just be the parallel line case. All right. Now, to distinguish between systems that have one solution or an infinite number of solutions, we take a look at, we have another word, another set of words to define these. Basically, if you have two copies of the same line, we call those dependent equations. So dependent equations represent the same line. Okay, so dependent equations represent the same line. So that would be this scenario here. Then we have independent equations. And independent equations represent two different lines. Okay, and so that would be the case where you have one solution and the case where you have parallel lines. So essentially what we have, if I wanted to do a quick summary here, the scenario where you have one solution would be considered a consistent system with independent equations. The scenario with parallel lines would be considered an inconsistent system with also independent equations, because they're different lines. And then finally, where you have two copies of the same line, we would call those inconsistent, I'm sorry, we would call those consistent systems. With those would be dependent equations. So that should give you a pretty good summary of all the different types of systems of equations that we'll be seeing in Chapter 11.